All right, happy Monday, everybody. We are going to do two more types of reactions today. We're going to do double replacement, which has a special little twist called a net ionic reaction, and neutralization here. Before you begin this video, please make sure that the sub has given you the solubility chart that you need. The solubility chart is a side that has S's and AQs on it, so make sure when we are referring to that, we are on that side of that piece of paper that she has given you. We are actually going to start with neutralization and then move on to the double replacement. We're going to treat this a lot like we did the notes on Thursday, in that I'm going to go through a couple of examples with you, and then you will finish these up with the remaining time in the period to practice these and make sure we understand what's going on. So when we are talking about a neutralization reaction, we should have down at this point that we are talking about an acid plus a base as my reactants, okay? And if we're looking at these next couple questions, we know that when we're talking about acids here and we look at all of these, they all have hydrogen in the front of their formula, okay? Acids will have hydrogens in the front of their formula. That's how we identify them. When we are talking about bases, we know their commonality is they have hydroxides at the end of the formula, because hydroxide is a negative ion. So hydroxide at the end of the formula means that you have a base. So we know how to look for that. We know how to identify that, even though it looks like a double replacement reaction. When we are done, the products of your neutralization reaction are always water and a salt. I'm going to put the salt in quotes because it's not NaCl every single time. Remember that a salt, chemically speaking, is any ionic compound, which means it's any metal with any nonmetal. Okay? So when we look at these neutralization reactions, we can see that all of them have the starting materials, the reactants that we need for a neutralization reaction. It does not matter whether the acid comes first or second in your reactants, as long as you have an acid and a base. You have to have both for this to be considered a neutralization reaction. When you are writing the products of this, and this is the same thing we're going to do with double replacement in a minute, we need to understand that these are really positive-negative pairs. Hydrogen acts as an ionic compound here, so it has a positive charge, and then whatever it is combined with here has a negative. So we're really just doing a switch, which is what we're going to do with double replacements in just a minute. Now that switch means that what's going to happen here is you are going to take your hydrogen, and we don't carry any subscripts across the arrow here. Your hydrogen will always go with your hydroxide. And if you look at this, that's going to be HOH, but we're not going to write it like HOH because that's not how we write water, but it is the same formula as H2O. And then once you've done that, you are finished with the hydrogen and the hydroxide. Hydrogen goes first because it's positive, hydroxide goes second because it's negative, and you're going to put together what's left over, okay? Now, what's left over has to start with your positive ion, with your metal, whatever was with the base. So check your charges before you do that. Na is +1, Cl is -1. So in this case, these can go straight together because they cancel each other out and you have a neutral compound. Now, what's also nice for this one is already balanced. So we don't have to worry about doing anything else there. Okay, we started off with that. Now, for your second one, you're going to have a little bit more work to do here, okay? Again, when I do these, I would always start by writing water, okay? Remember, you get a point for every correctly written formula. So even if you don't know what you're doing, but you know it's neutralization and you write water, you got a point, okay? Now, when you've written that water, understand that that always comes, I'm going to use a different color just so we can identify here. from your hydrogen and your hydroxide. So once you've written water, you are done with any of the hydroxides and any of the hydrogens. It does not matter what the subscript is. That 3 is there on this hydrogen because it is combined with phosphate, okay? So you just write water, you're done with those. And then you put together what is left. Now, what is left in this case, I'm going to put over here, is potassium. That should go first. Again, that's your metal with the base. You check its charge, it's +1. The other thing that's left is a phosphate. Now, this is a situation where I am going to take the subscript with me because PO4's formula is PO4. That subscript is part of the polyatomic ions formula, so it gets to go. So phosphate, and the charge on phosphate is 3. So your other product here should be K3PO4. Okay, and now that one's not balanced. We have neutral compounds, right? Subscripts first all the time, then we go back and balance with coefficients. So when we look at this, you would balance your potassium first. You would need a 3 here. And then the hardest part of balancing these is we got to make sure that we're counting all the hydrogens and all the oxygens, okay? So everything else except hydrogen and oxygen are balanced. Make sure you are looking at your hydrogens before your oxygens here, okay? I have right now 6 hydrogens. That means I need a 3 over here to give me 6 hydrogens. When I do that, I now have 7 oxygens on both sides. This is balanced and I am done. So your job in just a minute after you finish listening to this screen recording is to finish predicting and balancing these. Before we do that, we're going to talk about double replacement. Okay? So for this double replacement, we need that solubility chart. So make sure you have that out and flip to the side that has S's and AQs. As a reminder, when we are talking about double replacement, we will have 2 ionic compounds that are switching. I'm going to call this switching partners for now, okay? This is like going on a double date and both of you decide you'd rather be with the other person. Switching partners, and when you do that, you are going to form 2 new ionic compounds. Now, letter example-wise, compounds are going to be 2 letters together. So we would have AB plus CD. And just like we just talked about with the neutralization, if these are ionic, your first element is your metal, it's positive. Your second is your nonmetal, it's negative in both situations. If they're switching partners, A now has to go with something else that's negative. So it can't go with C. It has to go with D. So your new compound is AD. When you make your other new compound, that has to start with your positive ion. So C has to go first. It has to combine with B. Now, the other thing we're going to look at here is something called a precipitate. Definition of a precipitate is an insoluble solid, which is kind of redundant because solids are insoluble and soluble means it will not dissolve. An insoluble solid that forms when 2 aqueous solutions, okay, remember that means they look like liquids, but they are actually solids dissolved in water, when 2 aqueous solutions mix. So what I'm saying is you take 2 liquids, liquidy things, aqueous solutions, put them together, and you're going to, boom, get a solid out of there. Now, you will be able to tell me what these solids or precipitates are by using your solubility chart. It helps you predict when a precipitate forms. Precipitates are classified as solids on that chart. So anywhere you see an S, that means that it's solid. That means that is your precipitate. which we will also sometimes abbreviate as a PPT. Okay? So let's look at one of these sets here to figure out what your precipitate is. Here's how you use that chart, okay? We're going to say which of the following chemicals in each set is a solid precipitate. Again, that means the same thing. I only need to say precipitate. I'm just trying to get you in the habit of remembering that the precipitate is solid. You're going to circle the chemical that's a precipitate. So if we do A together, you are going to take a look at that, and your positive ions are on the left-hand side, so you're going to find sodium on there. You're going to put your finger on sodium. And then up top, you are going to find chloride. Put your finger on that. You're going to bring your fingers together, and when you bring your fingers together, you are going to see the letters AQ. That means that is not your precipitate, which means obviously your other thing in the pair has to be, but let's see what that looks like. Do the same thing with silver and chloride. When you bring your fingers together, you are going to see that S there. That S means that it's solid. That solid means that this thing is a precipitate. So I'm going to give you a second. I'm going to pause for a minute for you to figure out what the precipitate is in this second pair for letter B here. And then if we've checked both of those, we should see that the solid or precipitate here is zinc carbonate, because that's where you see the S. That means you have a precipitate there. Okay. All right. Now, you're going to do these on your own in just a minute here. But we are going to do these. You are going to predict and balance and write net ionic equations here in just a minute. Now, you will probably need more space to do this. So if you flip through your packet here with me and you keep going down past this, past all these practice problems, then you are going to come to a blank page, okay? So we're going to do another example here of a double replacement reaction. These will only be done with double replacement reactions. And we're going to do net ionic equations as well. So take a minute and write this down. The example we're going to use is calcium hydroxide plus sodium phosphate. And I'm going to remind you again, these are always ionic compounds, so you have positive and negative pairs. Positive and negative pairs. So when you write this reaction, I always just go left to right. So I'm going to take my calcium first, and I'm going to put it up here because I always have to check my charges. So when I check my charges, I should know, or I can look up that calcium is +2. And I understand that it can't be with OH anymore. I will not have a reaction. It also can't go with Na because that's positive, and you have to have a positive negative pair. So your only other choice here is the PO4. And remember, that 4 subscript can come across the arrow because it's part of a polyatomic formula. Okay, so that gets to come. Phosphate's charge is -3. 6 is your lowest common multiple. So to make this 0 or a neutral compound, I will need 3 calciums and 2 phosphates. Then I do the same thing with the 2 things that are left over, remembering that my Na has to come first. That is a +1. It will go with my hydroxide. This hydroxide subscript does not come across the arrow. It's not part of the hydroxide formula. It is there because calcium had a +2 charge. Okay, the only reason there are 2 of those is because I needed 2 to make that neutral. So then all I do on here, because that is a +1 -1, is NaOH. And then you are going to balance this equation. So when you are balancing the equation, again, we're going to do metals first. So I'm going to throw a 3 on this calcium and a 3 on this sodium. And then we're going to count our hydrogens next. And we would have 6 hydrogens here. So that's not going to work. Oh, actually, sorry, let's do our phosphates next. We're going to throw a 2 here. And then you have 6 hydrogens and 6 sodiums. So we're going to change this. This is one of those that has to go back and forth a little bit. So this is your balanced reaction. Now, on these, we are also going to add states of matter or phase notation using your solubility chart. Okay, so we're going to look at calcium hydroxide here to start. When you start, these will be aqueous. Sodium phosphate and calcium hydroxide are aqueous. So if you look those up just to make sure, and that's the way it's listed on all of your practice problems up above. And then you're going to go to calcium phosphate. And when you go to calcium phosphate, you're going to notice that that has a solid, so you're going to put a little S here. When you go to sodium hydroxide, you're going to see an AQ. So I'm going to circle this right now because I need you to know and understand that because you said this was solid, this is your precipitate. So if I asked what the precipitate was in this reaction, you would say calcium phosphate. Okay? That is important for what we're going to do next. So what we are going to do with this now is break this down even further to see what's actually happening on a molecular level. So we're going to write a full ionic reaction first. Okay, and this is going to bring in something from your ionic covalent. And that means that we're going to look at this and we are going to dissociate anything that's aqueous because we know that in an aqueous solution, an ionic compound dissociates or breaks apart. Now, we got to pull everything in here, our coefficients and everything that we have when we're pulling this apart. So first, I'm just going to break down this calcium hydroxide. Again, dissociate means what is it made up of? And you can kind of figure that out from I have calcium with a +2. And then according to this subscript here, I have 2 hydroxides to start, okay? So this is another situation where should you put the AQs? Yes. Am I going to count you off if you don't? No, not right now. Okay, I'll tell you where this is going to become a problem. Now, what we didn't do before is we did not have coefficients because we did not have reactions. We only had single compounds that we're breaking down. That 3 has to be applied. So what that 3 means is that I actually have 3 calcium ions. And because there's a 3 and a 2 here, I have 6 hydroxides. I'm going to do the same thing with my sodium phosphate because it is also an aqueous solution. So again, if you want to start by saying, okay, I have 3 Na pluses, just the formula, not the coefficient right now, plus 2 PO4 minus 3, we can do that. Oh, shoot, that would just be PO4 minus 3 if we're not using the coefficient yet. Okay? Then you have to put the coefficient back in, which is where that 2 came from. And then I actually have 2 times 3 there, so I have 6 sodium ions. Okay, these again are also aqueous. Okay, good news. When we get to the precipitate, we don't have to break that apart. If it's solid, that means it doesn't dissociate. That means that the ions are more attracted to each other than they are to the water, so they're actually going to stay together, so we get to do that. But then we have to dissociate the sodium hydroxide. So you're going to have 6 Na plus 1. I'm pulling the coefficient in right away right now. 6 hydroxides, and those are aqueous. Okay? This is going to feel like a really long process. The first couple times you do it, it gets faster as we learn it. Okay? So this is a full ionic. This is all the ions that are hanging out in the beaker or whatever container you have right now. What we have to do now is find spectator ions. spectator ions are kind of what they sound like. If you're a spectator at a sporting event, you are not participating, you are watching. So these are ions that don't participate in the reaction. And we'll know they don't participate if they are the same on the reactant and the product side. Okay, so if I look at this, what's the same on the reactant and the product side? I have 6 sodium ions over here. I have 6 sodium ions on the reactant side. I have 6 hydroxide ions on the product side. I have 6 hydroxide ions on the reactant side. Now, what is left over is called your net ionic. So the only thing that's really happening in this beaker to make this reaction occur is you are taking your 3 calcium ions and they are super attracted to your 2 phosphate ions. And these were aqueous. This is where we have to have the AQs. This is a must in your net. And they will be more attracted to each other, so they will form your precipitate, which is a solid. Okay? Now, you can go straight to the net ionic equation. If you know how to do that, do it. If you have no idea what I'm talking about right now, don't do that. Start with the full ionic and go from there. But what you want to check when you're done, both sides should equal 0. Your precipitate is 0 because it's a neutral compound. It got that way because you have an equal number of positive ions and negative ions. If that is not the case, then you did something wrong here. Okay? All right, so just as a recap, this is your example. You need to, for tomorrow, make sure that you have predicted and balanced these 2 neutralization reactions. And for these 2, 3, and 4, you need to predict, balance, and write the net ionic equation. There is not much space here, so you might want to do these on another piece of paper. Or if you want to do it on your iPad, that is fine with me too, as long as they are done, okay? Also, your lab is due tomorrow, so hopefully you already did that. But if you didn't, both of those things need to be done, to react or not to react, and all of this. All right, tutoring's available if you're super lost. I will see you all tomorrow.